Welcome. Uh, my name is Hania, and in this article, we will talk about methods to solve linear programming problems with analytical geometry techniques. As mentioned in Hiller and Lieberman, a medical programming model is simply a linear programming model with additional restrictions. As I know, mathematics has an initial division from which all its various branches are based: pure mathematics and applied mathematics. For the latter category, we can identify the many of the concepts from the pure part of this wonderful branch of science are taken as tools to support what is being estimated in each area of applied mathematics. Based on the aforementioned, we move to linear programming, which is the term to use to describe those optimization techniques in which the problems they represent can be represented as a linear equation. In general, these techniques are used more for a linear analysis and resources optimization. In some cases, we are limited to performing such analysis for resource optimizations. Then, in this research article, our following proposal will be represent a mixed integer programming model can be resolved using a point search with integer coordinates, from which start from the origin in Cartesian plane. As we mentioned, our general objective establish an algorithm for the automatical search of integer solution for flat regions, create from the inequalities that will form the solution region, with the aim optimization linear programming models for decision variable integer x.
Now we have the approach. I am Talais Damian, and this is the approach for the proposal of this problem, which is to determine an automatic solution search algorithm for integer programming problems. We will first explain what it consists of emphasizing a linear programming in this article. Now, this is going to be resumed. This linear programming model is objectivized on the real values of the objective variables. Now, we have the graph of a LPM in R2, and this is contemplated on real values of the condition variables. As we can see in the previous figure, we haven't touched the graph stretched lines in the ellipse of the solution polygon. We are constraints. The solution polygon that encompasses all the possible real solutions of the model. Then we have the model. This is a model that only has two condition variables. This has its function objective, its model restrictions, and the non-negative condition. Graphically, is going to sketch the line representative of the objective condition, so it passes through certain points. We can identify it on Desmos. You click the link that is over here. Now, what we are proposing in this article is to establish that the maximum solution of a linear programming problem posed in a form like this is given by the vertex of the solution polygon, whose normal distance from the origin to that point is the maximum possible normal distance. Remember that in R2, a normal distance is obtained like this. Then we have a new proposal formula that is based on a linear equation like this one. We have to remember first that this is the general form of a linear equation in R2, and of this depends our normal distance that we are going to solve like this. If you want to consult this, please take the annexes of this article. Now, this is the new model of our objective solution. Considering that the above is the equation of a line, we use the slope of the line to generate a parallel line with the special characteristic that it passes through a specific point P0. Thus contains the general equation given by this one. And these are the previous values considered for the model. And this is the proposed formula. And now we repeat that you want to consider this, please take the annexes of this article. This is a maximum value of Z, but this is not the solution of the problem. We have to remember that this is only a criteria for having the maximum value of Z, but it's not the maximum value, it's not the solution. From the above, how we can be sure the maximum value of Z is given? It's too easy. Let's reduce to the Euclidean geometry and the concepts of this. The value of Z is directly proportional to the normal distance d from the origin to a straight line with this slope, which implies that the longer of the distance, the greater the value of Z, and vice versa. Viewed graphically is like this. This is the geometric comportment. Now, this is the condition of our article. The conditional variables has to be integer, they are, and graphically we will take only these points for having an example. And applying our alternative proposed, this is the algorithm. First, identify the points. Now we have to know that for effects of the proportional formula, they have to be integer. Then, in the second place, we have to apply the proposed formula. Then, in the third place, we have to verify which is the point or what are the points with the maximum value of d in the proposed formula. Remember that this is the normal distance. Now, in the last point, we have to substitute the values of the one or all the points that obtains the previous step in the objective function of the problem in order to obtain the maximum Z. And these are the limitations of the problem. The first limitation of the proposed formula and the alternative problem is, first, this problem has only the horizon of R2 and not for Rn for n major of 2. But this is open to having more investigations in the future. But the second is that this proposed formula is only applied for maximum optimization, not for minimum optimization. But if you remember how is the dual theory of optimization problems, we can take this for having our proposing formula and having the solution in this way. But now, we have an application for having the conclusion of this. Let's assume that this is a new programming model with the special condition that we have to have all the integer x. Now, we apply the steps first and second of the proposed algorithm, and then we have this figure. In this one, we have the solution area, we have the conditions, and we have the points that has only integer values for the solution into the region. Now, we are going to evaluate directly the values of these points in our proposed formula and compare against the values of Z obtained for each one. And now we have the next table. These are the points. These are the values of the proposed formula for everyone, and these are the values of Z for everyone. And now we can check that we are having the maximum of Z in the maximum value of the proposed formula. And now we are going to say that this is not the solution, but this is an indicator for, say, in this point, we have the maximum value of Z, where we have the maximum value of the proportion formula. And as can be seen, the value of the maximum Z also corresponds to the value of the maximum value of we were talking about before. So our criteria is valid. For this example, the optimal solution would be like this: 5, 0, and 15%.
As we could see, the criterion of the normal distance to a straight line in the plane was correctly taken to be suitable to obtain the solution of integer programming problems. It is worth noting that the obtaining of the element d is not a parameter that directly influences the outcome of the integer programming problem. However, it does serve a parameter to take a criterion on the possible solutions of the problem, but it can rule out later methods such as decision trees to solving problems of this type. Truth is remains open to the reader the creation of an algorithm to search for integer coordinate points within a given solution region so that in addition to making integer programming more aware with these proposals, it is now fully automated.